Okay, right. So let me discuss the example number 5 and 6, right? So I have worked through the examples and I already upload this sheet in the VLE. So you can download that one, and at the same time you can refer that document with the lecture. So I hope you will be able to understand how to work on these examples, right? So let me look on the example, right? So the example number 5, so this should be number 5, right? Number 5, say the consider steam power plant operating in a simple ideal Rankine cycle. Steam enters the turbines, right? So the steam enters the turbine at 3 megapascal pressure and 350 Celsius and is condensed in the condenser at a pressure of 75 kilopascal. Determine the thermal efficiency of the cycle. So what is asking is the thermal efficiency of the cycle, right? So let me work on this thing. Okay, so so let me draw the four components, right? So the four components are, we have the boiler, right? So the boiler and the turbine, condenser and the feed water pump. Okay, so boiler is where the heat is in, right? Q in, and the turbine we can get the work out, and the condenser Q out, heat out, excess heat out, and the pump work in, right? So let me name 1 to 2 as the pump action, 2 to 3 as the boiler, 3 to 4 and the turbine, and 4 to 1 as the condenser, right? Then we can draw that diagram in the TS diagram, right? So this is our famous curve, right? I hope you remember how we get this curve, right? And then the cycle is look like this, right? So you know this cycle operate in two pressure, right? We have high pressure line, right? So we have this side high pressure, right, and this side the low pressure, right? Then what is turbine, what is enters to turbine is high pressure vapor, and what is exit from the turbine is low pressure vapor, right, if you remember. So let me draw the diagram. So the boil action start from, so the pump action 1 to 2, right, starting from the saturated liquid to 2, right, up there. This is the isentropic compression, right? 1 to 2 is isentropic compression. Then the heat addition in the boiler, right, Q in. So 2 to 3 is the heat addition. So you have the Q in here, right, Q in, right? Then 3 to 4 is the isentropic expansion in the turbine, where we can get the W out, work out, right? Then 4 to 1 again Q out, heat rejection, Q out, heat rejection, that is constant pressure heat rejection. So isentropic compression, constant pressure heat addition, isentropic expansion, and constant pressure heat rejection, right? So these is our pressure line. So you have the high pressure line going like this, right, and the low pressure line going like this, right? Okay, so that's the data which given by the question, right? So let me refer the example. So it says the steam enters the turbine at 3 megapascal and 350 Celsius, right, and condense in the condenser at 75 kilopascal. So we know high pressure is 3 megapascal, low pressure is 75 kilopascal, and the temperature of the superheated steam, that means where the steam it enters the turbine, is 350 Celsius, right? So let me draw that one. Therefore we know P3, pressure at point 3 and pressure at point 3 should be equal, and that is equal to 3 megapascal, right? There is no. Then temperature T3 is 350 Celsius, it is given, right? So 350 Celsius, therefore T3 is 350 Celsius. Then also we can say the condenser pressure is 75 kilopascal, therefore P1 equal to P4 equal to 75 kilopascal, right? So those things we can extract from the question itself, right? Then what it is asked to is find the thermal efficiency of the cycle, right? So we can write the equation for thermal efficiency. So like theta thermal equals to W net over QE, right? So this is known. So W net means the total work that given by the cycle. That means W out. So the W net we can write W net equals to W out minus W in, right? So where the W out, so we get the W out in turbine and W in the pump, right? Therefore we can write W out is equal to, so this is the W out, right? And this is the W in, right? So this is the W in here, and this is the W out. So we can write the W out equal to H3 minus H4 and W in as the H2 minus H1, right? So that is what is written in here. Okay, W out equal to H3 minus H4. That's been enthalpy at point 3 minus enthalpy at point 4. Likewise, W in equal to H2 minus H1, and the same time we can say W in equal to V delta P, right? So this is the compression action. Therefore, we can write V delta P, right? V for specific volume and delta P for difference in the pressure, right? Then so if we can find these things H1, H2, H3 and H4, we can find the Q out, right? So sorry, W out, we can find the W out, and we can W out and W in, therefore we can find the W net, right? So one part is okay. Then the next one we have to find the Q in. So the Q in is the boiler action, right? You can see the boiler action. Boiler in boiler 2 to 3 is the boiler, therefore we can write H3 minus H2 is the Q in, heat in, right? So that is what is written in here. Q in equal to H3 minus H2. Okay, all right. Now our task is to find H1, H2, H3 and H4, right? If we can find those things, then we can find the neta, right? So where we start, so where what is the best place to start is the point that we know all the parameters, most of the parameters, right? So therefore we know the point 3. So the point 3 is the one that we are interested in, because we know the pressure P3 and also we know the temperature T3, right? And also we know that point 3 should be in the superheated region, right? Therefore we can refer the superheated table to find the H3 enthalpy at point 3. Okay, that's right. Let me go back to the property table. So in property table you can find it here, superheated steam, right? So these are superheated steam. Okay, A6 is superheated water tables, right? So you can find that A6 table, right? So here we have the superheated table, right? So the pressure is 3 megapascal and temperature is 350. Therefore we can go back to the pressure. Now if you look on the superheated table, you have the pressure here, right? Now pressure here. Okay, now you have the pressure here and the pressure likewise, right? Then you have the in column wise you have specific volume, right? So this specific volume, internal energy, enthalpy and entropy, right? Okay, now let's find the 3 megapascal pressure. Now we have here so pressure is 3 megapascal, we have that one here, and temperature is 350, right? So we are currently referring to this line, right? Okay, pressure is 3 megapascal, temperature is 350, right? So with that we can straight away get the enthalpy as 3116.1, right? So this is our enthalpy. Okay, why it is? Because the third column is the enthalpy, right? So we have the specific volume, internal energy, enthalpy and entropy. Therefore column 3 is the enthalpy, right? So the value that one is we are interested in is right, so 3116.1 kilojoule per kilogram. So we can extract that value from here, right here, and can write H3 equal to 3116.1 kilojoule per kilogram, right? And the same time we can extract the S value, right? Now since the T4, that means the turbine is a isentropic expansion process, therefore entropy at point 3 should be equal to entropy at point 4, right? Therefore we can straight away write S3 equal to S4, and we can find the S3 value from the table itself, right? So this is the S3 value, right? Okay, so this is the S3 value 6 point. Okay, so we are interested on this line, right? Okay, now this is our 3116.1 is the enthalpy, 6.7450 is the entropy value, right? So we can extract that value and say S3 equal to S4 equal to 6.7450, right? Okay, right? So S4 is known, S3 also known, right? So we have found the H3 value, therefore H3 we have known. So the next thing is to find the H4 value, right, in enthalpy at point 4. Now how do we can find that value is by accurately estimating where this point is, right? Now we already know the S4 value, that's mean entropy of that point 4, right? Entropy equal to this much, right? Then the next thing is we have to figure it out where this point lies, right? Now we know this point should be in this pressure lines, 7.5 kilopascal line, sorry, 75 kilopascal line, but it is hard to say where this is. It can be exactly on the saturated line, or maybe in the superheated region, or maybe in the mixture. Now this is the mixture, right? So we have the mixture region, saturated line, and the superheated region, right? How do we figure it out where this point is, right? Is by comparing the S values, that means entropy values, right? Now we can refer the table to figure out this value, that means entropy at point 1 and also entropy at this line, at this point, right, saturated point, by using saturated tables, right? Now let me refer the saturated table under the pressure 75 kilopascal pressure. Okay, now we are referring saturated table, so this is saturated pressure table because the pressure is given and pressure is 75, right? Pressure is 75 kilopascal. So this is pressure, so we have the 75 kilopascal line, so this is the one that we are interested in right now, right? Now let me look at these values. So we have the pressure in this column and the saturated temperature. For that particular pressure we have saturated temperature, so that is this column indicate, and then we have specific volume, right? Specific volume of liquid fluid, Vf for fluid and Vg for gas, right? That means specific volume for liquid, specific volume for gas, right? Then we have internal energy, enthalpy and entropy, right? In this case you can see we have Uf for fluid, we have internal energy for fluid and internal energy for gas, right? Then in between we have Ufg, that means basically Ug minus Uf. So what's the value in here is basically this value, that means the Ug minus Uf. So we can refer that one as a operative energy, right, basically. So likewise we have internal energy, enthalpy and entropy, same thing, right? So Hg for in this case, right, in enthalpy we have Hg, Hf, that means this is enthalpy for fluid, then this one enthalpy for gas, and then the difference, right? Likewise we have the entropy as well. Now we are interested on the enthalpy at point, now let me go back, we are interested in enthalpy at this point as well as this point, right? So this is liquid and this is gas, right? So you can extract that values from here, enthalpy. So Hf is 380 84.44, right, fluid, and the enthalpy at gas is 2662.4, right. So we can extract those two values and we can write in this equation, right, in this manner, right. So I have write in this H value, right, 384.44 and 266.2, right. So this is our enthalpy value. The same way we can extract the entropy values as well, right, entropy values. So the entropy for the fluid is 1.2132 and the gas 7.4558, right. So so I have written those value in here, right, entropy value. Then we have to check whether our S4 values either in between of these two value or beyond this value, right. So what is our S4? So this is our S4, right. S4 is 6.744 and our SF is 1.21 and SG is 7.4558. Therefore we can clearly say this value is means between these two values. Therefore what we can say about these two is that this point should be in between these two values, right? That means this point should be in the mixture region, right? Otherwise if you do not get this kind of relation, then if you get, for example, let's say you have the S4 larger than the 7.4558, this means it is in the superheated region, right? But in this case it is in the mixture region, where because we have that point in between our saturated two saturated values, right. Now the next thing is we have to find what is the portion of that one, right. So let's we get this portion as the x, right, x. Then we can write x equal to this value 6.745 minus this value. That means this length divided by this whole length, right. Okay, that is what is done in here. 6.7450 minus 1.22, that means this length, right, divide by 7.4558, that means this value, minus this value, the first value, right? So if you do the calculation, you can get 0.8861, right. Okay. Now we also say this is this value as the quality of the steam. Now this is the quality of the steam, right. We call this value as the quality of the steam. If you ask the question like what is the quality of the steam in the turbine exit, that means you have to calculate for this value, right. Since we know the quality, right, then we can find the x value. That means this is H4 value, right. So therefore we can write H4 equals to x time this distance, x time the total distance plus this value, right, I mean this value. Okay, so that is what is done in here. So the H4 equals to x time, so this is the x time this value minus this value, right, plus this value. Okay, that is what is given. Therefore we can write H4 equal to 2402.851, right. So that way we have found the H4 also. Right now, up to now we have found the H3 and H4. Okay, right. So there's another two more to go, right. Let me check what is the next value. So up to now we have found H3, that means this value, we have found this value H3, H4. So the next one is H1, right. H1 is quite easy because it is in the saturated line. Therefore we can simply refer the saturated table and find this value, right. So let me refer the saturated table, 75 kilopascal line, and we know saturated HF fluid is 384.44, right. So therefore we can write this straight away from the table. H1 equal to 384.44 kilojoule per kilogram, right. So the next thing is how we can find the H2, since H2 minus H1 is the work in, right? So H2 minus H1 is the work in, and also we can write that one is a V delta P, because this is a compression work, right? So this is isentropic compression, therefore we can write V delta P as the work in, right? So therefore we can say H2 minus H1 equal to V delta P. So what is V? V is the fluid, volume of the fluid. Now why it is fluid? Because we are in this point. So this is 100% fluid, right? So this is 100% fluid, 100% liquid. So we are compressing from this point to this point, right? Therefore this is, we have to take the volume of the fluids, right? So let me refer to the tables. So we are in the 75 kilopascal line and we are referring to the VF, right? So this is the VF. Okay, so the volume is 0.001037 specific volume of fluid, right? So therefore we can write in this V equal to, sorry, V equal to 0.001037 multiplied by delta P. Delta P is 3 megapascal minus 75 kilopascal. Therefore 3 into 10 to the power 3 and 75. So this is, we have converted all the things in the kilopascal, right? Therefore we can calculate this one, right? Then H1 is known, therefore we can find H2 equal to, while doing this you can substitute the H1 value from here, right? Then we can find the H2 value, 387.437 kilojoule per kilogram, right? Okay, so far we have figured it out, H1, H2, H3 and H4, all the things, right? Then we know all of that, then we can calculate for the Q in. So the Q in is H3 minus H2, so all the values are known. You can just calculate the Q in. So Q in become 2728.627 likewise. We can calculate the W net as well. So the W net equal to H3 minus H4 minus, so this is work, so this is basically work out and this is work in, right? So you know, so we have calculated all the values, therefore simply substitute that one and we can find the W net equal to 710.26216. Then same way we can find the neta value by substituting those value. This become 26.02 as a percentage, right? So that is the neta value. So that's how we can work on this example, right? Okay, so the next one is example number 6. So it's quite similar problem, right? If you have understand up to this point, I want you to pause stop the video and work the example number 6 on your own, right? Then after that check with the answers, right? Okay, let's work with the example number 6. So let me read it out. So Noracholi power plant is the very first coal power plant in Sri Lanka, which produces 900 megawatt of electric power. It has a 3 turbine where each turbines produce 300 megawatt of electric power. Assume that the power plant operates on an ideal Rankine cycle with turbine inlet condition of 5 megapascal and 450 Celsius and the condenser pressure of 25 kilopascal. The coal has a heating value. That means the energy released when the fuel is burned is 29,300 kilojoule per kilogram. Assume that the 75% of this energy is transferred to the steam in the boiler and that the electric generator has an efficiency of 96%. Determine A, the quality of the steam at the turbine exit, the mechanical output of the turbine, the overall plant efficiency, then the required rate of coal supply for one turbine to produce 300 megawatt of power, right? So let me draw this one quickly in the diagram, right? So this is how it look like, right? So we know now if we divide this way, you know this is, so from this point we have the high pressure and this way we have the low pressure, right? Likewise you have the boiler where the Q in, turbine Q out, condenser Q out and pump work in, right? So the high pressure is given as 5 megapascal and the low pressure as 25 kilopascal, and also we know the temperature at point 3 is 450 Celsius, right? Okay, so the first one, part A, asking the quality of the steam at the turbine exit. What is the quality means? So this point, we are talking about this point. What is the fraction? So you remember the x value. So basically asking what is the x value at point 4. So so this we already known, right? P3 equal to P2 is equal to 5 megapascal, T3 equal to 450 Celsius, P4 equal to P1 equal to 25 kilopascal. So the same thing. So let me refer, the first thing to find is the H3 value, right? So let me refer the table, superheated table, because we know this should be in superheated region, right? Therefore we can refer the superheated region to find what is the H3, right? So the pressure is 5 megapascal and the temperature is 450. Therefore we can refer to the superheated table here. Right, we have to refer 5 megapascal, right? So we are in this one, right? So this is 5 megapascal, right? And the temperature is 450, right? So this is 450 in this line, right? This row. Then we can say these are the value that we are interested in, right? Okay. So the specific volume is this much, internal energy is this much, entropy and enthalpy. So we can extract the enthalpy value 3317.2, right? So that is what is given in here. H3 equals to 331.17.2, right? And the same way we can refer to the S value as well, entropy 6.8210, right? Therefore we can write S3 equal S4 equal 6.8210, right? Why it is S3 equal XO? Because we know this is isentropic expansion where the entropy is constant. There's no entropy change in isentropic expansion, right? That's why we can say S3 equal to S4, right? So likewise, then we have to figure it out where this point lies. Therefore we have to find the value in here, entropy value in here, as well as the entropy value in this point, right? Then we can figure out where this point 4 lies, either on this line or beyond this line, right? For that one we can refer to the saturated table under 25 kilopascal values, right? So let me refer to the saturated table. So this saturated table, and our okay, so pressure is 25, so pressure is 25 kilopascal. So we have the 25 kilopascal line here, right? Okay, so this is our, so this is the line that we are interested in, right? Therefore from that one we can find SF, yes, right? This value SF and the SG, right? So SF is 0.8932 and SG 7.8302, right? So that is what is written in here, right? Then we compare that two values with the S4 value, this value. Therefore we can surely say the 0.4 is in between these two lines, right? So likewise we can find the X value. Therefore the quality of the steam is the X equal to this value, that means this value minus this value, this get this length of this line divided by this value minus this value, again the length of this line, right? So that way we can get the fraction equal to 0.8548. So that is the quality of the steam. So what you mean by so what is the mean by of this one is you have 85% 45% of steam in it, right? So you have the mixture, that means you have steam as well as you have the liquid, gas and the liquid both, right? So the what is the percentage of gas is 85% 45, right? Then what is the percentage of liquid? That means 100%, 100 minus 85.45. That is the percentage of liquid. Right? Percentage of gas is 85% 45. That is what is mean, the quality of the steam, right? So that is part A. The quality of the steam is that one, right? And then part B. So what the part B is, the mechanical output of the turbine, right? So we know that means the Q out is asking for, sorry, the work out. So the mechanical output is this, right, in the turbine, W out. What is the W out? W is simply H3 minus H4, right? That is H3 minus H4 is the mechanical output, right? So therefore we can simply say we know this. So we already know the H3 values, right? H3 value we have figured it out from the table, right? H3 value here, okay. Okay. Right. Then we have to find the H4 value, right? So since we know the percentage, I mean know the quality X value, therefore we can write this equation, but before that let me extract the H value for saturated region from the table, right? So, okay, let me go to the our tables, right? And we have to extract H values. So we have to extract the HF and HG. So under the 25 kilopascal pressure, so the HF value is 271.96 and the HG value is 2617.5. So those values are the values that are written in here, right? 271.96 and 2617.5. Right? Then therefore we can write the equation for H4. H4 equal to X time. So this is X. So this is X time, right? So this is X time 2617.5. This value minus this value, right? That is the fraction plus this value, right? That means all the way up to here length, that is 271.96 plus this length. That's what this means, right? This plus this, right? Okay. Then we get H4 equal to 2276.223, right? Kilojoule per kilogram. So so we have figured it out the H3 and the same time the H4. So therefore we can write the W out equal to H3 minus H4, which become 1040.97 kilojoule per kilogram, right? Okay. That's the part B. Then part C asks for the overall plant efficiency. That means the ratio of the net electric power output to the energy input as the fuel, right? So that means the overall plant efficiency, not the thermal but the overall, right? So we can write the overall plant efficiency equal to thermal efficiency plus thermal efficiency multiplied by boiler efficiency multiplied by electrical efficiency, right? So in the question, boiler efficiency is given as 75%, electrical efficiency is given as 96%, right? The next thing we have to figure it out is the thermal efficiency, right? So like the previous question, we can write the thermal efficiency is W net divided by Q in, right? We already found, so the W net equal to W out minus W in divided by Q in, right? So we already found the W out, right? We had to figure it out the W in and less the Q in, right? So Q in, we can write Q in equal to H3 minus H2, right? Because that is the boiler action, right? We go back to the table. So this is where the Q in, right? So this is the Q in. This is where the Q in is, right? Therefore H3 minus H2 is the Q in, right? We already know the point 3, H3, H4, but we don't know H1 and H2, right? So the like previous case, we can figure it out those things by using this equation. So the W in equal, sorry, Q in equal to H3 minus H2, and W in is equal to H2 minus H1, and also it is equal to V delta P, because this is the compression, isentropic compression, right? So from the table we can find the H1 value, right? So because H1 is here, right? It is, so this H1 is here because it is on the saturated line, exactly on the saturated line. Therefore we can refer to the saturated table and we can extract the H1 value, right? So let me go back. We are interested in this line, 25 kilopascal line, and the H value, HF value. So the H value is, HF value is 271.96. So right, so that is what is given in here. H1 equal to 371.96 kilojoule per kilogram. So the same way we can write W in equal to H2 minus H1, and the same way we can write it is W in equal to V delta P, because it is a isentropic compression process, right? Therefore we can write V delta P, V for specific volume liquid, right? Specific volume liquid. So we can extract this value from the table, right? So 25 kilopascal line, VF specific volume for fluid equal to 0.001020, right? So that is what is given in here, right? In here, right? Then delta P is 5 megapascal minus 25 kilopascal. Therefore we can say 5000 minus 25. So when you calculate this one, you will get 5.0745 kilojoule, right? Kilojoule per kilogram. Okay. Right. Therefore we can write the W in equal to 5.0745, right? Likewise. So the same W in we can write it is equal to H2 minus H1, right? Since we know the H1, right? So this is H1. We have extracted the H1 value from the table. Therefore we can write, solve for the H2 equal to, from this equation, equal to 277.0345 kilojoule per kilogram, like this. Okay. Then we can calculate for neta thermal, right? We know all the H1, H2, H3 and H4 values. Therefore it is simply subtraction. That means we know, so this is the W out, this is the W in, right? Then this H3 minus H4, right? Then we can calculate that one as 34.07 as a percentage. Okay. So since we know the thermal efficiency, then we can write for the overall efficiency. So the overall efficiency is boiler efficiency. So this generator efficiency, thermal efficiency and the boiler efficiency. So it was become 24.53%. Okay. Then the final part asks the required rate of coal supply for one turbine to produce 300 megawatt power, right? So let me approach in this manner. So let me first look on what is the final energy conversion for 1 kilogram of coal. That means if you burn 1 kilogram of coal, what is the final electrical energy we can get from that one, right? So if you burn 1 kilogram of coal, it say 29,300 kilojoule per kilogram will be emitted. So you can multiply that value from our overall efficiency, then we get this value. That what is this mean is, if you burn 1 kilogram of coal, you can get 7,887.29 kilojoule per kilogram of electric power. So this is basically the Q in, right? Q in, and this is the electric power output, right? Overall electric power output. Then to find the required rate, you can simply divide that value. So this is our 300 megawatt divided by our energy per kilogram, right? Then you can get the overall rate. So overall rate is 41.74 kilogram per second. So this is per second, right? Per second you have to burn 41.75 kilogram of coal to produce 300 megawatt of power, right? So that's how we can work on these examples.